Okay, so lastly, I gave you guys kind of 3 informal outcomes. Come on, don't go away, board. There you go. I gave you 3 informal outcomes of the things we had to do. Let's do and review those real quick. First thing is there are 4 types of functions we have to learn about. We've got your square root functions. We've got your fraction functions. Then we're going to get to exponents, or Mr. McCarthy is going to do that one, and logarithms. Okay, so those are the 4 main things we're doing. You can kind of break each unit up into the same sections. The main concepts are you need to know like how do I describe this? You need to know like the details about how they work, like the background info. Right. So like for example, tell me something that you should know that's unique, specific to square roots. What's kind of a unique property about them? Sure, can't use negatives. Right, that'd be a good example. Whereas, give me a unique property that's specific to rationals. What's unique about something that's written in a fraction form? What's like a... Sure, you can't let the denominator be 0, right? So we're going to have some specific details you need to know about exponential and logarithmic graphs that are kind of like that, like some of the restrictions, if that makes sense. So we'll start with that. The second thing you need to know is what the basic graph looks like.
Technology hates me. It's just so good with technology.
Okay, so you need to know what some of the basic graphs look like. So right off the bat on this particular screen right here, this is your basic square root function. Okay, so hopefully you kind of know what the basics look like. But you should also know how to transform it around so that if you wanted to put this graph like way down here, like that example I gave you was, there you go. You'd know how to maneuver that. And then, do you guys remember the third kind of thing I need you guys to be able to do?
Remember from last day?
Yeah, you need to be able to solve them. Okay. This is going to be kind of underneath basic graphs. Okay. So I'm actually going to continue with a little bit more work on how these graphs look. This board to work, but it's just killing me here. Okay. So I've actually bolded a word in our notes here. Today's topic is we're going to learn how to take the square root of a function. I want to make sure I'm clear on the terminology here. I'm not talking about the square root function. The square root function is this like shaped graph. What we're going to talk about today is how to take a pre-existing graph and square root that graph. Let me give you an example. Let's say I give you the graph of x bracket x plus 3 bracket x minus 2. Would you guys be able to roughly know what that graph looks like in your heads? Hopefully after our first unit you know that this is a cubic function with a root at 0, a root at -3, and a root at 2. So you'd know that it roughly has, I don't know, a shape. Let's see, you'd have one there, one there, one there. It roughly should have like a shape like this. What we're going to talk about today is how to take a function that currently exists and throw a square root sign over top of all of it, and what that does to a graph. Okay, so the square root function would be like the root of x. And I mean, you could consider it to be like, say, the root of 3x, or what you're doing is you're squishing it in 3 times. You can do that as well. But today I want to see what happens when we throw a square root sign over top of other functions. For those of you guys who are doing calculus, this is like a composition of functions. Or like if I asked you to take the square root of, like, say, log of x. We haven't learned what a log is yet. But like the same principle applies where there is like a function literally inside the square root sign. Is that clear? So this is not the square root function that looks like this. This is taking a pre-existing graph, and around that pre-existing graph, we're square rooting what's there. I'm going to try moving again so this thing can go rich. Okay, so let's talk about some of the nitty-gritty details first. So when you are square rooting a function, we should talk about the term invariant points. We've used this vocabulary before. Invariant means a point that doesn't change, right? So let's talk about what happens when you square root a number. If I square root the number 4, it becomes 2. Let's only count the positive half, right? Why aren't we including the negative number? What would that cause a problem with? If it could be 2 or -2, it's no longer a function, because it would then fail the vertical line test, because you can't have 4 give you 2, but also give you -2, which is why you only get, like, say, half of the graph. Okay. So 4 drops down to 2. Square root of 1, though, what would that be? 1. This is an invariant point, right? Because when you square root 1, it stays 1. The other invariant point is the square root of 0, which stays 0. These are the only 2 things that won't move, 1s and 0s. Because when you square root them, they stay what they were. If you were to square root 9, it's not 9, it's now 3. If you square root 0.5, it's not going to be 0.5, right? So hopefully that's kind of the first logic here. Your invariant points will be at 0 and 1. And I have to point out, though, we're talking 0 and 1 for what y is equal to. Remember, what we're going to do is we're going to take a function, and we're going to square root that function. So what we're doing is we're taking a y value and square rooting it. So you see how right here, my y value of 1 is the same on both graphs? And here my y value of 0 is on both graphs. I'll make sure it's clear. It's not the x value that stays the same, it's the y value that stays the same. Okay, let's try an example. And I want to have you guys practice composite notation because kids struggle with this. So I'm going to write in the form g bracket f bracket x. What I'm really saying is throw this f of x function underneath a square root sign. So it's a fancy way of me saying I'd like for you to square root 2x plus 1. Everybody clear on that? Kind of how that's fitting together there? So the function that we are square rooting is 2x plus 1. So I'd like to start by doing that. What would the graph of 2x plus 1 look like? Well, it's linear. Tell me something about that linear graph 2x plus 1. What point is easy to plot? That's a 1. And then it's got a slope of 2, right? So with a slope of 2, over 1 up 2, over 1 up 2, over 1 up 2. That should roughly do it. Okay. So this is what 2x plus 1 would look like. But what we want to graph is g of f of x, which is the square root of 2x plus 1. You see how we're just, this is the square root of a function. We are square rooting the 2x plus 1 function. So based on what I just showed you a slide ago, there are 2 points that I should be able to plot on this graph immediately because they're not changing. When it's 1 and when it's 0. Okay. Consider this graph right here. The y value is 1 right here. So when I square root that y value, it doesn't move. Where's the other point that's not going to move? Which is also known as the, you're saying, yeah, your x-intercept. Yeah, this x-intercept won't move either. These 2 points won't be moving. Because when you square root an output value of 1, right, like this is your output, this is your y, right? Well, then when you square root your y value right here, it doesn't change when y is along the line for 1 or when it's along the line for 0. So those are our 2 points that don't change. Then there are 3 other segments of graph we have to consider. We have to consider the segment of graph, which is greater than 1, which is basically, which is basically this section right here. We have to consider what would happen right here. We have to consider the segment of graph, which would now be between 0 and 1, which is this small little section zoomed in here. And then we have to consider the section of graph, which is less than 0, which is everything in the negatives. So let's start with the section that's in the negatives. All of these y values here are negative. What happens when you try to square root a negative? You can't. Which means that all of these values right here, there really are no x values that are going to show up in my new graph right here. This point right here is literally going to be the last point that I can work with. this value right here is a y value of -1. I can't square root a y value of -1. Right here is a y value of -3. I can't square root a y value of -3. So everything that's in the negatives, basically you can't work with that. It's not possible. So that was actually the easiest one to do. Once you figure out your invariant points at 0 and 1, everything that was below the axis just ceases to exist. Now let's talk about the points that are up here as your y values get larger. What happens when you have a y value, like say right here, of 9? What happens when you square root that? It becomes 3, right? So this value right here of 9 is going to drop down and all of a sudden be right here at 3. What used to be 9 is now at 3. The other value that would be really useful is right about here. What's special about this point that I'm trying to point out right here? Right here's the point I'm looking at. What's special about that? Right, y is 4, which means at this point right here, come on, it's going to drop down to about 2. Long story short, when you square root numbers, 9 becomes 3, 4 becomes 2, 100 becomes 10. I'm doing this with my hand right now to show you that when you square root a number, they always become smaller. So whatever this y value is right here, it becomes shorter. Whatever this y value is right here, it becomes shorter. You know how like we had our list of transformations? This is number 12 on our list of transformations. You could times the graph by 3. You could make the x's negative. You could flip x and y around. Another thing you could do is you could square root a function. And what it does is everything that used to be a large value becomes much smaller. And it causes the graph to start taking on this shape like this, where all of these taller y values are gotten smaller. Here's the hardest section. What happens when you square root a fraction, like a decimal value? I'll just do an example here. What happens if I were to square root a fraction like 0.5? Does it get smaller? Actually, it gets bigger. This is an anomaly that most people don't really know of. They don't spend much time thinking about this. Oh, it's driving me nuts. I'm just going to sit here again. We'll get there. I were to square root, come on. Okay, so apparently I lost half the video. Hopefully it works. The point I was trying to make before I lost connectivity here. Okay, forget it. I'm getting there. When you square root a value, is this something you guys have seen before? If you square root a decimal, okay, if you square root a decimal, like say 0.2, it actually makes it bigger. Is this something you guys have seen? Right, like normally when you square root a number, it makes it smaller. 8 becomes 2.8. Or if you square root 900 and 789, it makes the value smaller. If you were to square root 0.789 though, it doesn't make it 0.28. It actually makes the value larger than where it began. This is an anomaly most people aren't aware of. Here's what this does to our graph then. All of these values right here that are purple, that are very small, the graph actually becomes larger. And if I could zoom in just on this section right here, what we had essentially is one point that was right about here, and another point that was right about there. And we used to have a straight line like this. What it ends up doing with our new graph is it causes it to look like that, where the old values right here, the new values, once you square root them, actually get larger. Okay. However, once you get past the point 1, these numbers up here, where the y value is 2 and 3 and 4, then when you square root them, it actually brings them smaller again. So when y is bigger than 1, it actually shrinks the graph, but when y is smaller than 1, it actually like increases the graph. And this is basically where our graph shape came from then, where it has this sort of shape to it like we've been talking about before. So now I can actually explain why the graph has the shape it does. All right, last thing, let's talk invariant points, domain, and range. Where are invariant points? Well, I can promise you the invariant points will always end with 0, and they'll always end with 1. Because y values of 0 and 1, when you square root them, they don't change. So where is this point right here? This one's 0, 1. What about this one right here? Where's that at? Where's the x value for this one? Negative 0.5 or negative 1/2? It's not at negative 1, it's the halfway in between point. You know another way I can figure this out? Take a look at this equation up here. It was 2x plus 1 under the square root sign. However, one of the things that I've been harping at you guys for the last while is you always have to have it factored. Is 2x plus 1 in a factored format? No, but I could write it in a factored format. If I factor out a 2, it would leave me with x plus a half. Make that connection? Normally we wouldn't bother factoring out a 2, but I could. I could factor out a 2. It would leave me with x plus a half. What does plus a half do to a graph? It slides it backwards that way by half a unit, thereby explaining why this point is now over there. You see how that comes together? Okay, what's the domain of this graph then? X is greater than or equal to negative 0.5, yeah. And your range is y would be greater than or equal to 0. So far, so good? Lost you too bad? Okay. Okay, well, let's try a different graph now. Let's sketch the graph of what's a quadratic graph, and let's talk about what would happen if we were to square root that graph. So, x minus 2x plus 1 as a square root graph, that would have an intercept over here at 2, an intercept over here at negative 1. It's probably going to look roughly, I mean, I don't need to have the exact picture, but it's probably going to look roughly like this. There. It's not bad. Let's try this again now. Okay, so let's talk about invariant points. We are now going to square root this quadratic graph. So the invariant points, we're going to have 4 of them. I'm going to have one of them right here and one of them right there, because that's where your y value is equal to 1. And what I'm really asking you to do is square root your y value. The other invariant points are going to be the intercepts themselves, right here and right here. Those points aren't going to move. Does that make sense? Okay, then you have 3 other regions of the graph to consider. You have the regions of the graph where y is less than 0, which is basically where the bottom loop of the parabola happens to be. Essentially what happens here is if you try to square root these y values, which are negative, you physically can't. So based on that, there literally is no graph here. So I sometimes just put a big X here just to remind myself that like I'm not even putting anything there. And then I focus on the part of the graph where it's getting larger, like right here. Here my y values are getting larger. What happens when you square root a number like 9? Well, 9 would drop down to 3. 4 would drop down to 2. All of these points are now going to be shorter than their red partners. Right? Like all of these red points have been dropped downwards because when you square root a large value, it becomes smaller than it used to be. That same logic then applies over here on this side as well. All of these points will kind of fan out this way because they're all getting compressed down by a factor of a square root. Your 9s become 3s, your 4s become 2s, your 100s become 10s. And then for this little itty bitty in between section, I mean, if you could zoom in, really what's happening is for a short period of time, the purple graph kind of goes around the red graph. Does that make sense? Because all of these have y values which are decimal numbers, but when you square root a decimal number, it actually makes them larger. So it should kind of go over top. So it actually crosses twice in there. Like it actually has two intersection points. Long story short, this is what the graph would look like on your calculator. So I'm actually going to bring that into the equation now. So I am going to square root, and then in brackets, I'm square rooting x minus 2 and x plus 1. So it kind of has that shape that I was kind of expecting to it there. But do you see how right here in the middle, there's this big gap? If I were to go to my table of values, you'll actually notice that all of these guys have values, and then error, error, error. Oh, okay, we have values again. And so basically everything that would have gone below the axis right here doesn't work. Now some kids would look at this and say, oh, only the numbers 0 and 1 don't work. But that's not really true, because it's not just the numbers 0 and 1 that don't work. Like negative 0.5 was a problem. Negative 0.6 was a problem. Negative 0.99999 was a problem. You know what I'm saying? So like the errors in my graph are basically from negative 1 up until positive 2. X could not be those values. Can I see how I wrote that there? Basically, I'm telling you where x is not allowed to be. From this negative 1 all the way up until that positive 2, we have issues. I mean, even try it. Let's say I plugged in 0. 0 minus 2 would give you minus 2. 0 plus 1 would give you 1. So 1 times minus 2 would give you minus 2. But then you'd want to square root that. Yeah, do it. So now we probably wouldn't write this in this notation. We'd write it a little bit differently. And I want to remind you of something called interval notation, which I'm sure I've shown you before, and I have a whole ton of slides later in the notes on. So can you guys find some slides where I talk about interval notation? Oh, I don't know, where is it? Here it is. Can you guys find this? This is interval notation. It's a shorthand way of writing your domain and range, to write it a little bit faster. Essentially, the idea is you write it like an ordered pair, and the first digit is the lowest number you can have, and then the second digit is the highest number you can have. Do you guys recall this? You guys are using this calculus right now. Do you remember doing this at all? Okay, well, let me give you the full rundown then. If the lowest number you can have is 0, and the highest number you can have is 20, you just write 0, 20. This is not an x-y coordinate pair. It's just telling you how low it goes to how high it goes. Now, if you're allowed to use the number itself, like if you're allowed to use 0, use a square bracket. If you're not allowed to use 0 because it's like one of the less than signs, then you use like a rounded bracket. Let me show you some examples, and then we'll go back to the one we just put on. Let's say that you were allowed to go from 0 to 4. 0 is permissible, but 4 is not permissible because there's an open dot. This notation will be written as 0 to 4. You'd use a square bracket around the 0 because you're allowed to use 0. And then you end with a curled bracket around the 4 because you can't actually use 4. You can use everything up to 4, just not 4 itself. Is that all? If you ever need to go all the way like as far left or as far right as like say infinity, you can write say negative infinity. You guys know the symbol for infinity, right? The side of the 8. You can use that symbol if you want, but we always use a curl parenthesis here, just implying that you can't actually reach infinity, because infinity is not a number, it's more like a concept. Here's another picture slide that I have kind of indicating the same thing. If you're going from like say A to B here, you use like say a square bracket like that. And fast forward this slide. what would the domain of this graph here then be? This graph goes as low as -5 and as high as 7. But see how I've got an open circle here at -5? That means I can't actually use -5, so I'd use a curl bracket there. But I can use 7 because 7 is filled in, so I would use a square bracket at 7. And that's like your fancy way of writing domain and range. Honestly, this is the exact same thing as -5 less than x less than or equal to 7. It means the same thing. It's just this one's kind of like the shorter notation. Now that I've kind of gone through that, does this ring a bell? Ever doing this at all? Often what I would do is on previous questions, I'd say like your domain is -5, 5. That just means that like set your window size from -5 to 5, right? Like when you go to your window, just make this be -5 and make this one be 5, and that's what this notation means. The one more thing I need to add to this is, I don't have it in the slides here, so let me go back to the one we were working on now. Where does this graph exist? Well, it exists in two places. Really, there's this section over here, and there's this section over here. So what I could do is I could say, well, this graph keeps extending forever to the left. It really is extending from -infinity up until right at this spot right here, which is at -1. Now, infinities always use a round bracket. That's just a convention. Infinity is not a number. You can't include infinity. But -1 right here, can you use -1? Like, is that value a closed dot or an open dot? It's a closed dot, because could you use -1? Yeah, it just means it would give you 0, but you can square root 0, so you would use a square bracket here. And then you have a big gap. And whenever you have like a gap in your graph, the math symbol for that is a U. And U stands for the word union, where it basically means that it can be in this section here, or we'll pick it up again in the future. Right? And so then the next number that you're allowed to start again with is right here, and that's the number 2. 2 is the next number where you can validly start again, and you can then go from 2 all the way until you get to positive infinity. And this would be a shorthand way of writing your domain. So I need to prep you guys for this because they've been throwing this on the diploma more often. I feel like they're throwing it on the diploma just to see whether they can fool and trick kids. Because another way of writing it would be this. They could have said like x is less than or equal to -1, and x is greater than or equal to 2. So you could have written it using this notation here just as easily, and that would have made sense. But they're testing you on integral notation to make sure you know what it is. That's your domain. What's your range? That'll work, yeah. Your range, basically the lowest you can get to. It's doing so good. I had like a good stretch there where it didn't break. Your range is going to be from 0, because that's the lowest you get to in terms of your y values, up until positive infinity. You can have 0, but you can't have positive infinity. The range of one of these graphs should never be below 0 unless you like manipulate it afterwards, right? Because you can't square root a number and have it end up in the negatives. Well, and not have it still be a function. Still okay? Have we lost anybody? Okay. Okay, let's move forward then. So let's talk about the theory behind this then. When you are square rooting a function, the domain is going to be similar to the original function. Here's how it works. If the original function was positive or 0, you're good. Right? If the graph was above the y-axis, you can square root it. However, when the graph was below the axis, the graph can't exist there. So there will be certain gaps in your graph. The range is pretty much positive or 0, right? Because when you have a graph, like even like say a graph like this, what ends up happening is this section here you can't have. This section here you can't have, but right here I can square root those numbers. And right here I can square root those numbers. So your range is pretty much always greater than 0. So then here are some of the other nitty-gritty details. If it's less than 0, it can't work. If it's exactly 0, then it remains at 0. That's that invariant point, right? If it's between 0 and 1, the graph gets slightly larger. That would be like on that zoomed in version right here that we were working on. The graph actually becomes slightly larger for a little while there. Then when it receives 1 again, it's actually at the same point. And then after 1, then it actually gets smaller. So here, nothing exists. Here's an invariant point, doesn't move. Here the graph goes above the original graph. Then it's back to the same point as the previous graph. And then the rest of the points all get squished downwards, which is why square root graphs usually have this shape to them. So there's the theory behind it. Here's some more, but let's move on. Let's see if we can sketch what the square roots of these functions would look like then. And I'm just going to do this really roughly. Okay, so I'm going to go a lot faster than I did before. I'm going to look for all of the x-intercepts. Like say this one right here and this one right here. Those ain't moving because x-intercepts are defined when y is 0. And then I'm going to look for these points right here where y is equal to 1. Those points aren't moving either. Then I'm going to look for where the graph was negative. Well, here it was negative, and here it was negative. Nothing's happening there. So I won't even draw anything there. Let's just erase that. Then I'm going to look for where the graph is positive and large, like say right here. This value is currently at 4 for y. It's going to get dropped down to 2. And then I'm going to kind of connect the dots. All of these values that are kind of like the highest crest right here, they're all going to drop down and become smaller because that's what the square root does. It makes values smaller by a factor of whatever the square root is. What's going to happen in this little section right here, though? I get what you're saying there, Jamie. It kind of goes like around the outside almost, and it gets kind of slightly larger. What we've essentially made here is this graph is giving us like a semicircle. You see that? Like it's actually made like half a circle more or less. Okay, let's do domain and range. I believe this point is at 1, and this point over here is at 5. So the fast way of writing domain and range would be 1 inclusive to 5 inclusive. You guys follow that? What about our range? What's the lowest number for y we can ever achieve? 0. Now, this graph doesn't go upwards to infinity, though. It does have an uppermost limit. Uppermost limit is that? Good job. Does everybody else follow that? The uppermost limit was at 4, but it's dropped down to 2. Okay. This would be an excellent numeric response question. They'd give you a picture of the graph. They would say, I'd like for you to square root the function, and then they would ask you, where is the domain and range from? And then your final answer would be like, say, 1502 as a numeric response answer. You get what I'm saying there? Let's try this one here. So do the same sort of process. Start by finding where you have your x-intercepts, because those guys ain't moving. Why don't they move? X-intercepts are where y is 0, and when you square root 0, it's still 0. The other points that you're going to have are anywhere that x is equal to 1. And you have one of those right here, and right there. Those points aren't moving either. Those are your invariant points. The next thing I focus on is where is the graph negative? Because where that graph is negative, the new graph just won't exist there. So like this section here and kind of this section here, there won't be any graph because you can't square root those y values. And then what I do is I focus on y values that I can square root that are very large. Like say in this section right here. Right here it's at 4. I'll drop it down to 2. And then right here again, it's at 4. I'm going to drop it down to 2. And this is at 5. 5 doesn't square root to an even number. It'll square root to like 2 point something. So it should give me kind of a little rise there. But you see how it's smaller than the old rise? Because all of those got square rooted. And usually you can kind of like fill in the gaps and realize that like along the edges here, it actually is like over the top of the other graph, but this should work. And then over here, I have a similar concept. This will kind of come around the top of this graph, and then it's going to keep going upwards infinitely. Like it's going to keep getting larger, it looks like, but it'll always be a shorter value than the previous y value. Let's assume that this graph does continue going for forever. I'll put an arrow on it. Let's assume that it does continue moving here. What's your domain? You want to take a stab at it? What's the lowest number you can have? -4. Keep going, Michael. Not to infinity, because from -4, it goes all the way up here till it gets to 2, and then there's a gap. So you got to go -4 to 2, square brackets for both, union, because then there's going to be a gap, and we're going to pick this up again on the other side of the gap, which is at 4, and then positive infinity with a curl bracket, just because positive infinities are always curls. You good on that? Sweet. Okay, what's your domain, or what's your range? What's the lowest y number possible? Inclusive 0, yeah. And then how high will this get? If I draw an arrow on this here. Infinity, yeah. I mean, it will keep going higher and higher, right? Eventually, this graph here would have gotten to 100, which would get this guy to 10. And eventually, this graph would have got to 1,000,000, which would have got this guy to like, well, actually, I'll put choice. Anyways, you get the idea though, right? It will drop down, but it will continue getting larger and larger and larger based on square rooted values. So, you guys feel like you can handle that? Okay, cool. Why don't I leave these ones here for now, just to save us some time, because I feel like you guys seem like you have the grasp of this, right? But I mean, just for like the rough version, it would have looked something like this and like that, because really this would go away, this would go away. This one right here would have looked something like this, and then it would just literally have a dot right there, actually. Actually, I should talk about the second one here. Can you guys see why there would literally just be a dot sitting right there? Because when it touches the 0 axis, it would be able to be square rooted. You can square root it there, right? But on this side right here, well, you can't square root those negatives. And on this side right here, you can't square root those negatives either. Right? So this graph would actually look like this. It would be like a semicircle right over here, and just a single dot sitting right there. Strange graph, eh? Right, but that's what we're getting into. Our polynomial functions are very standardized and normal. Our non-polynomial functions start to look funny. They have different unique properties to them. Okay, let's try a different type of question. What if I gave you coordinate points? Could you figure out the new function if, essentially I'm asking you that same notation here. What I want you to do is I want you to square root all of these coordinate points. Let me do the first one for you. 0, 4 would become 0, 2. How did I figure that out? I know. Well, not square root them both, square root the y value. Good question, a good thing to point out here. I kept the 0 the same, and I square rooted the y value, so the square root of 4 is 2. 1 root 1 negative 5. Will this point exist on the new graph? No. Because can you square root negative 5 as a y value? No, it would have been below the axis, so that one's out. What about 2? What would 2's new y coordinate point be? What'd you get, Brad? That'll work, 2.8. What'd you do? You typed in, so why don't we just call it the square root of 8 then? I mean, 2.818 or whatever it is fine, but chances are you'd write it as 2 root 8. or even better, 2 and 2 root 2. You guys see how I got from the 8 to the 2 root 2? Do you guys remember how to do that? You need a quick tutorial. I'm seeing your nodding heads. Do you want a tutorial on this? You good? Okay. I want to point out, 2 years ago, Carlin and Raj, their grade, I was so mad on a diploma because they made a question B to answer it in like a numeric response format. And when they answered in numeric response format, they put in like 2 and 8, something along those lines there. They actually put like 2, 1, 8, I believe, because they assumed the number in front was a 1. And they put an 8 inside there, but that wasn't how they wanted it to go. They wanted it to be 2, 2, 2, because the 8 can actually reduce to a number in front. And I thought that was so cruel because they knew completely how to solve the question, and root 8 was not incorrect, but they had reduced the root 8 to a 2 root 2. And they got that one wrong. Like, I felt bad for them because like they both knew what they were doing, but so. Anyways, I point that out to kids now. Okay, what about 3 with 9? What's that going to turn into? 3 with 9 will turn into 3 with 3. 4 with 0 will stay at 4 and 0 because 0 square roots to 0. And then 5 and negative 2? Not existent. Yeah, it won't exist. So, you guys can see here how this would be another way of phrasing the diploma question. Right? I think I've shown you a couple different ways now that they can maybe ask you a question. This would be a great numeric response kind of thing, where they'd want you to then type in, like, say, these points right here are like 3, 3, and 4, 0 or something. Right? Like you can make a numeric response. The other thing about doing it this way here, you can't type it in your graphing calculator. With other equations, what you could do is you could just say, well, the equation happened to be 5x plus 7. Well, I'll just literally type in the equation of 5x plus 7 and get a graph picture of it, and then you can work with it from there, right? But if I just give you random points, then you can't use your calculator. Okay, this guy right here is then leading back into that domain and range interval notation thing here. So I've got this graph right here, and I want us to algebraically determine the domain of this thing in interval notation. This would be a great type of question I could ask. I could make it numeric response even. So let's talk it through. You can actually type this in your graphing calculator, so what the heck, why not? Let's type it in since that is possible. We want to square root negative 2 x plus 3 x minus 2. And then let's just get a typical graph of it. Okay, I guess that's what I have. Why would it look like this? Well, now let's consider this graph a little bit more. This graph right here would have been quadratic. It would have been an upside down quadratic with roots at minus 3 and at 2, and it would have roughly had this sort of shape to it. Well, all of your negative values over here just wouldn't exist, and then all of these values here would just become a little bit shorter than they were before, hence the semicircle that I'm seeing here. Right. So for the final answer, this could have been numeric response. They could have said, write it in the form A, negative A, comma B. Right? If I asked you to write the domain in the form negative A, comma B, the domain would have been from negative 3 up until 2. Does that make sense? Because those were where your intercepts were. They also, in theory, could have asked you what the range was. The range is going to be 0, comma something. I don't know what the something is off the top of my head right now because I have to figure out where the highest point happens to be here. But the range would have been 0, comma something because the lowest the range was at was 0. You see how I could have made this a 4-digit multiple choice question? It could have been 3, 2, 0, and then however high this gets. I don't know how high it gets, but you guys can find that, right? Okay, cool. Okay, then the rest were all my slides basically on this interval notation, just so they're familiar with it. So low number, high number. I feel like you guys have the hang of it, so let's fast forward through these all. Why don't we do this very, very last one, then we'll call it a day. Negative 24, comma 9 is a point on the graph of f of x. I do not know what that function is. It could be linear, quadratic, cubic, quartic. It could be a square root function. It could be a logarithm or exponent. We have no idea what the graph looks like. I just know where that point is. I want you to tell me where it's getting moved to after all of these transformations take place. So negative 24 comma 9 would be way the heck over here. Let's talk through all the transformations we'd have to do. What's this negative 2 going to do it? It would flip it and make it twice as tall. So the negative 2 would take the point and put it way down here. It's still going to be at negative 24, but what's its y-coordinate now? 18. Nice, negative 18. Good. Okay, now I got to approach bed mass in the right order here. I also need to square root that value and add 1. You know what I just realized here? I did it in the wrong order, didn't I? Because can I square root it now that it's at negative 18? No, I did it wrong here. This square root right here really should take precedence, right? Because really, you know how there's bedmass, brackets, exponents, multiply, divide, stuff like that? Really, this, do you guys remember what a square root is as an exponent? That's the power of 1/2. So actually, we should have taken care of the exponent part first. So I take it back. I shouldn't have moved it to here, because I can already see why that would cause me an issue. I can't square root the negative 18 number, but I can square root the 9. So let's start with that. Let's do it the square root version first. If I square root 9, it would pop it down to become 24 and 3. Well, that accounts for the square root. Then after I've accounted for the square root, now I can deal with the negative 2. So let's see, the 9 gets square rooted down to 3. Then it gets times by negative 2, so it's at 24 and negative 6. And then according to BEDMAS, we've accounted for our brackets, we've accounted for our exponent, we've accounted for our multiply. Now we can finally account for our add, and we're going to shift it up 1. So it's going to be at 24 and minus 7. You guys follow that train of thought? I'm going to do that next, okay? Because everything inside the bracket will now change it side to side, right? So what I was doing is I was dealing with all of the stuff that was going to go in the vertical direction. So the square root would affect it vertically. The minus 2 would affect it vertically. And the plus 1 is going to affect it vertically, which is why I've always been sitting on the line of 24.
You don't have to do the adding class.
Well, we'll do that, but we'll do the adding for the horizontal dimension last next.
It's negative.
Right, because, yeah, good catch. Yeah, I did that on purpose. Yeah. Okay, so you guys are with me that in terms of the vertical direction, this is where we've now finished in terms of anything that happens vertically. Okay. So then as I was talking to Brad over here, we do need to do the factoring. So this will be 3x minus 2. So now in the horizontal direction, we still have to do things in the right order. So I have to apply the 3 first and then the minus 2. So the 3 will squish the graph inwards. So it's still going to be at a value of minus 5, but if I squish it in by a third, the 24 is going to come back into a... These are all minuses, by the way, aren't they? It'll squish it into minus 8 and minus 5, right? I've squished this inwards 3 times. And then lastly, the minus 2 slides the graph over 2 more units. So it should be at... Final answer, negative 6, comma 5. I say that train of thought one more time. 24, 9. 9 gets square rooted down to 3. Times it by negative 2 to drop it down to negative 6. And the plus 1 pulls it back up 1 to minus 5. So that accounted for the negative 2, the square root sign, and the 1. Those are all things that happen vertically. Then things that happen horizontally, we squished it in 3 times. We did not slide it over 6, though. We only slid it over 2. You guys able to follow that? Cool. Okay, quick summary then. Today's concept was basically, you can think of it as like one of the things that you'd add to your back of your pink sheet. You know how on the back of your pink sheet I was giving you all all the different things you can apply to a function, like putting a -2 in front or adding +1. This really fits better there than anything else, because what you're doing is you're taking a function and either you're wiping it out and it no longer exists because it's in the negatives. It stays in the exact same spot because it was either at 0 or 1 for your y values. It'll either become shorter or taller depending on whether it's a value less than 1 or greater than 1. And so now you should have the skill of being able to square root a function, which is different than the square root function. Similar concepts, right? But one is more of like, this is a graph that you're moving around, and the other one is more of an operation that you can apply to any graph. Questions? Okay. I hate to put you guys on a crunch, but tomorrow we're going to do fractions then. We'll do fractions Wednesday, Thursday. If it's okay with you guys, I may try to plow through all of topics 3 and 4 in one day. If you guys think we can handle it, I'm willing to try it. Which would then give you a work day back again on Wednesday. We could try that. And if not, we can just do as much as we could. Yeah, I mean, I split it up into 2 parts, obviously, because I knew it was going to be a long lesson. So we can try that by ear. Here's what you guys need to do then. The first assignment is online. Start working on that. Okay. Ideally, it would be great if you did it before you wrote your quiz. I won't make it due before you write your quiz because I know that is a short timeline, but it sure would be nice if you could try to have it done by the weekend, because it's your prep, right? It's what's going to get you ready for this. Okay, sound good? Okay, and break. You didn't know? But like it's, what time is it now? We set our clocks ahead now?
Yeah.
Yeah, so it's only like 2,
But I woke up
2:50,
before.
which was really 5. Yeah, let me just stop recording here.